very warm good morning, dear students. Welcome to these digital classes. This is your chemistry period, and as we have already started the laws of thermodynamic, and there are basically four laws: zeroth law, first law, third law of thermodynamic. In which zeroth law and first law of thermodynamic we have already done. Let's recapitulate once again. Zeroth law of thermodynamic is what? When a body A is in the thermal equilibrium with the body B and also separately with the body C, the body B and C will be in thermal equilibrium with each other. Let's understand with the help of this picture. If two bodies are in thermal equilibrium, suppose here A is thermal equilibrium with B and B is thermal equilibrium with C, it means that the C is also thermal equilibrium with A. Okay, so this is zeroth law. As A will be equilibrium with B, B will be with C, and C will be with A again, so it will remain zero. So law of thermodynamic, in first law of thermodynamic there are basically so many first law of thermodynamic, but energy can neither be created nor be destroyed, it only transfer from one form to another. This already we have done in that video. So okay, a very warm good morning, dear students. Welcome to this digital chemistry class. I would like to welcome you in this digital class of chemistry. As we have already done basic zeroth law of thermodynamic and first law of thermodynamic, and now I'm going to tell you about the heat capacity. And as name is already explaining everything, what is the meaning of this topic, that is heat capacity. So dear students, let me give one example to you. Suppose you are going to boil a water of 10 liter, okay, and if suppose you have one big gas burner, one small gas burner. So if you will put 10 liter in both the gas burner, just tell me in which gas burner the heat water will boil faster. Obviously the bigger one. Okay, it is somewhere the capacity of that gas burner which can boil heat the water mean faster than the smaller one. So it is called heat capacity. So capacity of heat energy which to raise the temperature of the system. So basically heat capacity of a body is the quantity of energy it needed to cause its temperature to change by 1 degree Celsius. The unit of heat capacity is Joule Coulomb inverse or Joule Kelvin inverse. The heat capacity is denoted with C, capital C, and formally we can write the heat capacity of a system is defined as the amount of heat required to raise the temperature. Please note down this definition in your notebook. Heat capacity of a system is defined as the amount of heat required to raise the temperature of the system through 1 degree Celsius. Once again, the heat capacity of a system is defined as the amount of heat required to raise the temperature of the system through 1 degree Celsius. The heat capacity is called thermal capacity also. So we can denote it with the help of the equation that C is equal to, now if I'll say C is equal to Q upon delta T, it shows that heat capacity is equal to the amount of energy raise 1 degree Celsius of temperature. So it become now Q is equal to C into delta T. The value become Q is equal to C into delta T. So if I will calculate Q is equal to C upon delta T become, so if I will calculate with the molar heat capacity, I will introduce molar heat capacity. Molar heat capacity of substance is defined as the amount of heat required to raise the temperature of 1 mole of substance through 1 degree Celsius. The equation become Q is equal to, now molar will also calculate with the C into delta T. So it become Q is equal to M into C into delta T. So now the C become specific
heat capacity. Heat capacity of a sample of a substance is the quantity of heat needed to rise its temperature by 1 degree Celsius. There are two types of heat capacities: heat capacity at constant volume and heat capacity at constant pressure. Heat capacity is an extensive quantity. For solids, Cp and Cv are equal, and for gas, Cp and Cv are different. Heat capacity is directly proportional to the amount of a substance. Q is equal to product of Cv and delta T, where delta T is equal to Tf minus Ti. The molar heat capacity of a substance is its heat capacity for 1 mole of the substance. The specific heat capacity is the amount of heat required to raise the temperature of 1 unit mass of a substance by 1 degree Celsius. Q is equal to C into M into delta T. Both specific heat capacity and molar heat capacities are intensive quantities.
We'll talk about specific heat capacity now. So specific heat capacity is what? It is the specific heat capacity or molar heat capacity when 1 mole of substance is going to be heat. Yeah, I can say molar heat capacity is the substance which is defined as the amount of heat required to raise the temperature of 1 mole of substance through 1 degree Celsius. Okay, so basically what is heat capacity? Now this is the equation we find out. Q is equal to M into C into delta T, whereas Q is heat energy, M is mass of, C is specific heat capacity, and T is temperature, which is changed in Kelvin.
Specific heat capacity. Specific heat capacity is defined as the ratio of the specific heat of a gas at constant pressure to the specific heat of a gas at constant volume. Its value represents the atomicity of gas. Monoatomic gases. Consider 1 mole of an ideal monoatomic gas at a temperature T and pressure P. The number of degrees of freedom of a monoatomic gas is 3. According to the law of equipartition of energy, average kinetic energy per molecule per degree of freedom is equal to half kT. Average kinetic energy of 1 mole of gas is equal to kT into N, where N is equal to Avogadro's number. Thus, U is equal to 3 by 2 RT, where U is the kinetic energy of 1 mole of gas. Du by dt is equal to Cv. Cv is equal to 3 by 2 R, but Cp is equal to Cv plus R. We get Cp is equal to 5 by 2 R. Hence, Cp by Cv is equal to 5 by 3. Diatomic gases. The number of degrees of freedom of a diatomic gas is 5. Cp by Cv is equal to 9 by 7. Polyatomic gases. It has 3 transitional and 3 rotational degrees of freedom. Cp by Cv is equal to 4 plus F upon 3 plus F. Cp minus Cv is equal to R is true for any ideal gas, whether monoatomic, diatomic or polyatomic.
So heat capacity of specific heat capacity can be calculated with the help of this numerical. How much heat does it take to bring a 3.5 kilogram iron fry pan from 20 degrees Celsius to 120 degrees Celsius? It means that what is M here? Mass is 3.5 kilogram. Heat capacity is 4.47 joule kilogram. Delta temperature is 100 because 120 minus 20 is 100. So it means that the equation will become 3.5 into 4.47 into 100, which will give 0.16 mole. So power of is equal to energy upon time. So time is energy upon power. You can calculate the power also. So in this equation, it become that when heat transfer from A to B and heat energy flow until equilibrium is not reached, heat energy lost by fry pan, heat energy is gained by fry pan. It means that it is net heat energy is 0. So now most important, that relationship between Cp and Cv. What are heat capacity Cp, Cb and C naught? The molar heat capacity Cr at constant pressure is representing Cp. At constant volume, the molar heat capacity is represented by Cb. So in the following action, we will find that how Cp and Cb is related to each other. So dear students, this slide is very important. The relationship between C and C for an ideal gas from the equation Q is equal to N. We know Q is equal to M C delta T. Okay. So at constant pressure P, Q is equal to N C delta T, and the which is equal to change in enthalpy. So Q is equal to N C delta T, or which is represented delta H. Similarly, in constant volume, Q is equal to NC now delta T, and here NC delta T is delta U. So we know that for 1 mole delta H is equal to delta U plus delta PB, which become delta U plus delta RT. When we will going to combine both equations, so delta H is equal to delta U plus R delta T. So when we will substitute C delta T is equal to C delta T plus R delta T, which becomes C is equal to C plus R. Delta T will be cancelled with delta T. So Cp is equal to Cp minus Cp is equal to R. It is Cp minus Cb is equal to R. Okay, this is the heat capacity, relation between heat capacity. So now the most important measurement of heat. How we can measurement? We can measurement the heat with the help of calorimeter, which is the process of measuring an amount of heat in a physical change, chemical reaction, or in transition of phase. A calorimeter is the tool used for calculating calorimetry. Generally, calorimetry refer to an experiment technique that we use for the measurement of enthalpy. Calorimetry technique is used to principle of thermometric method. So what is calorimetry? This is bomb calorimeter, which is used to measure delta U, delta H, or heat. Okay, so which heat capacity we are talking about? So we can measure those heat capacity on the basis of temperature. We can measure that what is the basic heat capacity of a particular amount, that we can find out with the help of this. So with this video is finished. So I think you understood the video. Generally, basically the question is coming the relation between Cp and Cb. It is very simple. So till my next video, take care, stay home, stay safe, and hope so you like this video. Keep enjoying digital class.